So our next speaker is Saar Bader from Oxford, who will be talking about group cohomology with Banach-based coefficients. Over to you.
Hi everyone. Welcome to stop me during the talk. Welcome to open your cameras. And I taught during Zoom, during COVID, as you can see. And yeah, just ask questions. This is a project with my brother, my dad, and Roman Sauer. So Saar Bader, Bader, and Roman Sauer. Yeah, I'll just start. So Kashdan defined property T such that it would satisfy two things. If you don't know what it is, those are the two things that are important. Higher ranked lattices in Lie groups have property T, and property T implies finitely generated. He wanted to show finite generations of lattices. What he actually did is he defined it as a topological property, and then you show that the Lie group has property T, and the property T goes down to lattices, and property T implies compactly generated. So for discrete groups like lattices, it implies finitely generated. Okay. The definition is that gamma has property T if for every action on an Hilbert space with almost invariant vectors, then there is an invariant vector. And I said it fast on purpose because I'm not going to use it. But you should know it. I'll give you three definitions of property T. One is that for every orthogonal representation without invariant vectors on a Hilbert space, an L2, it vanishes. There's a zero there. And L2, I would use the words Hilbert and L2, they're equivalent. Orthogonal means I preserve the norm. This is the same as the vanishing of the cohomology with LP coefficients for isometric. So it's like orthogonal when I don't have an inner product representation without invariant vectors where P is between 1 and 2. This was proved by Bader, Fuhrman, Gelander, Monod. Actually, they proved something for P equals 1, but they didn't manage to prove the full vanishing, and then Bader, Gelander, Monod proved, finished the proof for P equals 1. The third equivalent definition, don't worry, they will come back to us. They're like a Chekhov's gun. Every action on a median space has bounded orbits. Chatterjee drew to Haglund. The reason there's a space before the T is that there's supposed to be a thingy under the T, but it didn't happen apparently. This implies, I'm not going to define median space, but a tree is a median space. So this implies that every action of the group on a tree has a bounded orbit, but if you have a bounded orbit on a tree, you have a fixed point. And this is called property FA, the property that every action on a tree has a fixed point. This was proved much earlier by Watatani, but I just, so you'll see it all together here. Right, so Kushtan did everything for lattices. I want to talk, or for Lie groups, that was the motivation. I want to talk about that too. So we have a setup. G is a simple Lie group, think SLNR. Gamma is a lattice, so it's discrete, finite covolume. Think SLNZ. Don't complicate yourself. And me. And the rank of SLNR is n minus 1. Good. So Kashdan proved that in this setting, gamma has property T. I'm going to repeat what it means and show generalizations for the setting of lattices in simple Lie groups. So this implies that I go way too fast generally. Please stop me if there are any questions. This implies, so that was my first definition, my first equivalent definition is vanishing of the cohomology with Hilbert space coefficients. Okay, now generalizations for lattices. So here's a theorem of Bader-Sauer. The cohomology vanishes for not just in dimension 1, but in higher dimensions as well. All the way up to the rank, not including. Good. Another definition was that the cohomology with LP coefficient vanishes. And there's another generalization in the same paper of Bader Gromov. They show it for lattices in Lie groups for every P. So before we had P between 1 and 2, but for lattices we have it for every P. And now we take the join of these two theorems. So we showed that I kept the two theorems as they were and added a third. We showed that for lattices in simple Lie groups, the cohomology vanishes with coefficients in LP for every P and up to the rank. And I'm gonna say, I said it quite fast earlier. You can see there's the BFGM. Can you see my mouse? Nobody knows. And the BGM, and I said BGM helped to do P equals 1. And also for us, we have the complication of P equals 1 that we solve in similar methods to the Bader one, the BGM. Excellent. That's one generalization of two of the equivalence definitions. And it solves a conjecture of Gromov. So Gromov conjectured the vanishing of the cohomology up to the rank for the specific representation, which is called the regular representation, an LP of gamma, sometimes or most of the times you denote it by little LP, it doesn't matter. So this is gamma acts on itself, and so it acts on sums of elements of gamma with coefficients that are LP summable. And that is the specific representation where we take the coefficients of. Good. Okay, the third definition we have is that we saw that this implies that gamma has property Fa. This is, I remind you, so let me just define property Fan. A group has property Fan if every action on a CAD0 complex, I work with cube complexes too, but that's a different story. CAD0 complex of dimension n has a fixed point. So property Fa is also Fa1 because the only one-dimensional CAD0 complexes are trees. Every action on a tree has a fixed point. And it was conjectured by Farb that lattices have property Fan up to the rank not including. There's stuff to say about the not including. There are partial results of Frachik and Low. They showed for, I think, they showed for SL and Z, but not in the entire rank, or in the entire range, so not up to the rank -1. And I think now, not on archive yet, but they have other partial results. We are not sure what the optimal range would be. Farb did conjecture it for up to the rank -1, but maybe you have this property in higher dimensions as well. Okay, and this is actually how this project started. He knew about the Bader Sauer, so kind of the higher cohomology vanishing definition of T, or the stronger T. And in my master's, I worked with Neil Zarovich, master's advisor, and we defined a notion of a two-median space. And we showed that CAD0 two complexes are two median. So Saar thought maybe we could combine these two and show property Fa2 for lattices coming from groups with rank at least 3. And indeed, we could show. So what we showed is that vanishing with little L1 or L1 coefficients will imply finite orbit. Let me repeat this theorem slowly, because it's a very general theorem, and I will explain how it implies Farb's conjecture. X is contractible and dimensional simplicial complex, and I have a group action on it. And now I can choose a dimension and look at the ith skeleton in that dimension. One of them obviously needs to be K, but actually the theorem as stated here with the mistake is also true. It's enough that the ith cohomology group of the coefficients from the ith skeleton vanishes, but I meant that the cohomology would be the kth cohomology. So if the cohomology, the kth cohomology with gamma, L1 coefficients in the ith skeleton vanishes, then we get a finite orbit. In particular, given, so I think this is in the next slide. Theorem 1 plus theorem 2 will imply Farb's conjecture, because theorem 1 told us that the left side will vanish for gamma, a lattice in a simple E group up to the rank -1, because this is some L1 space. I mean, I gave a specific one because that's what I need for the theorem, but for a lattice, it's all of them. So I get a finite orbit. But Farb's conjecture was a fixed point. Well, in cat-zero spaces, if you have a finite or even bounded orbit, then you get a fixed point. From convexity, you should, if you do geometry, you should think of that. Okay, so we get Farb's conjecture, and I have time. Good. Okay, now I want to prove theorem 2 to you. So if there are questions so far, this is a good point. Good. So what's the setup? I'm denoting stuff. Delta I, as Hatcher denotes it, the ith simplicial chains in X. And I will need the delta -1 is R. And then you can complete it with respect to the L1 norm. I said earlier that we work harder to get P equals 1. And I also said that Gromov's conjecture was for P greater than 1. But we really need L1 for theorem 2. And I'll try and point where, and if you don't understand or you didn't understand, please ask me. So we complete with the L1 norm, and that's important. So we get little L1 of the ith skeleton. To calculate the cohomology with coefficients in V, we look at this chain complex coming from the bar resolution. Or this is actually the equivariant resolution. I don't think I'll actually use it. It's a very algebraic proof. You will see it's my first time using Beamer, and I made diagrams. You should be very proud. Okay. The theorem says that if the cohomology between 1 and n vanishes, then we should get a finite orbit. I want to use the negation assumption that the cohomology also vanishes at 0. Let me explain why it's a negation assumption. So the 0th cohomology is the invariant vectors. If it's not 0, then I have an invariant vector in little L1 of the I skeleton. How does it look like? It looks like an infinite sum, coefficient times simplex, right? And it's not 0, so there exists some coefficient which is not 0. Given that coefficient, there are only finitely many simplices that have that coefficient. And those must contain an orbit. Gamma must permute them to each other. So I have a finite orbit. So again, I explained why if the 0th cohomology does not vanish, then I do have a finite orbit. So if I'm assuming towards contradiction, I don't have a finite orbit, then also the 0th cohomology will vanish. It's important again because my proof is very algebraic, as you can see. I have this double complex that you can do with, there's this website where you draw them and then it translates it to LaTeX. Anyway, I have going to the left my coboundary maps, those that I use to calculate cohomology. But geometrically, I can go down with my boundary maps because my coefficients are k or I simplices, and I can just take their boundary. And the place where I use L1 is that this diagram extends as is to coefficients with the L1 completion of these coefficients. And specifically, this epsilon map in the bottom right will extend. Do you actually see my mouse, Gemma? Maybe can you tell me if I move it?
Yeah,
Yeah.
yeah, we
Okay.
can see it.
I will use it later. Good. So what happens is that here I'm assuming my space is contractible. So I know that if something going down is a cycle, I could feel it. But when I'll extend to the completion of delta, I will get L1 coefficients, and then I will know that my horizontal lines are exact. So I'm gonna play with these two. Let's start with my plenty of time. Good. I chose C0 here that fills up 1. Anything that goes to 1. And now, as diagram chasing goes, I have only one direction to go. Let's go left. And I did this fast. I went left and I went down. And it's a commutative diagram. In my map, this map is 0 because the action on R is trivial. Diagram is commuting, so I get that the co-boundary of C0, when you take its boundary, is 0. The space is contractible, so I can fill it by some C1. And that's the trick. That's what I keep doing. So I go left, I get C2, and I could fill it because, let's see it here. Okay, I did it fast. Jesus Christ. If I go left, I get C2. If I take it down, it must be 0 because it's like going twice to the left, or it's like taking co-boundary of the co-boundary of C0. Co-boundary delta delta is 0, no matter in which diagram I am. Okay, so I did this, I constructed everything by induction. I get Cn minus 1, I go left, I get something that's a co-boundary and a boundary again by this like commutation. I fill it up to Cn, I go left again, I get delta of Cn, that when I fill it, this Cn plus 1 must be 0. This comes from the fact that x is n-dimensional. So what I'm supposed to have here is Cn of gamma with coefficients in delta n plus 1. But delta n plus 1 is 0. I don't have any n plus 1 skeleton, which then means that delta Cn is 0, which means that Cn is a cocycle. Good, so now I need my rows. But in order to use something about my rows, I want to change diagram. So I complete the coefficients. It's in red because that's the main point. That's where I'm using L1. I complete the coefficients and now I can fill Cn. I fill it by something I call An. And then I go down because it's the only direction I have to go. And I get something that fills up. Again, I use the commutativity of the diagram to get that the image of the boundary of An and of Cn minus 1 are the same. So that's how I will construct my next cocycle. Cn minus 1 minus the boundary of An. And I can fill up that as well because my rows are exact. And I keep going and I keep doing that. And I'm gonna get to my contradiction. I'm excited. Okay. I found A0, which fills up the boundary of A1 minus C0. Okay, but A0 must be 0. It doesn't exist in my diagram, right? So then C0 minus the boundary of A0 is also 0, or sorry, the boundary of A1 minus C naught, the thing written here, is 0, meaning they're equal. But that can't be, right? Because epsilon of C naught, or which I called here partial boundary, is 1. But epsilon boundary or boundary is not. It's 0. So that is the contradiction. That is the end of the proof. I want to repeat what happened. I also want to say that this can be written as a spectral sequence argument. If you don't know what a spectral sequence is, it's a tool. It's a tool to do diagram chasing fast when you have a double complex like this. So what we did is we had our two diagrams. One we took with coefficients in the K-skeleton, chains in the K-skeleton, and one we took in the L1 completion of that. And we played with these two. Each time in one of them, the rows were exact, and in the other, the columns were exact. And just to complete the full recap of this talk, maybe I'll go back to ages ago, where I said theorem 1 and theorem 2. So we had the conjecture of Farb that we prove using this theorem that I just proved, plus theorem 1, which was general vanishing of cohomology with coefficients in LP up to the rank. And I think I will finish here.
Okay, thanks very much. Let's thank our speaker. Does anyone have any questions?
Can you say, I lost a moment when you said that if the zeroth cohomology vanishes, then you have a fixed point. Can you repeat that again?
Yes. So the zeroth cohomology are the invariants, right? So I look at my coefficients and I look at invariants. So if I have an invariant, then what is it as an element? It's some that is L1 summable. So I take its sum, AI, sigma I, where sigma I are all of the same dimension, it doesn't matter. And let's choose A1 that's not 0. And let's look at all the sigmas which have A1 as their coefficient. That must be finite, and gamma must permute them because I started with a sum that's gamma invariant. Yeah, thanks for that question.
I see. Thank you. That's cool.
Any further questions?
Good. Thanks for inviting me.
No problem. Let's thank our speaker again.